All right. Good morning, everyone.
Primo.
Everyone say hi to Heather. You've all missed her. Okay. Welcome to our Monday morning seminar. It is my pleasure to introduce Heather Watson. Heather went to the University of Toronto for her bachelor's, and then she went to RPI where she got her PhD with Bruce Watson, no relation, which she makes clear on her CV.
Yeah, he's not my dad.
He's not her dad or uncle or grandfather or anything. And then she moved on to here, and she was a postdoc fellow here for 2 years. She worked with Faye. We did not overlap. I missed her just by a few months right before. She was Liz's office mate. We did not overlap either.
Good times.
That's right. And then she moved on to Livermore, where she did another postdoc with Rick Ryerson. And then she moved to Northern Illinois, where she was an assistant professor, and then moved again, hopefully for the last time, to Union College, where she's now an assistant professor as well. And she's right now on sabbatical, so she's very happy. And we're really glad to have her back here. Heather is an expert in experimental metrology, mineral physics, planetary science. She studies transport properties within the Earth and other planets, other planetary bodies. She focuses on electrical conductivity measurements and on diffusion. So today she'll tell us about diffusion.
Great. Well, thanks, Annette. Thanks for inviting me here, and thank you all for being here. It's nice to see everyone, and it's great to be back. It's actually been several years since I've been here at the Geophysical lab, but it's great to see and meet some new people and also see a bunch of old familiar friends. So yeah, thank you so much. The last time I gave a talk here at the Geophysical lab was actually probably my interview for a postdoc, where I also talked about diffusion in sulfides and metals. I've done a bunch of different things in the last 15 years between then and now, but somehow I found myself coming full circle to do similar experiments, but kind of addressing a different problem than I did back then. And so what I'm going to talk to you about today are experimental measurements of diffusion in sulfides and metals with specific applications in iron meteorites, and in particular applications to the closure of important isotopic systems in meteorites, and what that can help us learn about the early evolution of planetary bodies in the first few million years of our solar system. So part of this introduction might be kind of basic, but I just want to make sure that everyone is on the same page when we're talking about diffusion, because maybe not everybody here thinks about it quite as often as I do. Some of you do, but maybe not everyone. And you just want to remember that diffusion is an ongoing process at an atomic level that happens in all kinds of materials that have a temperature, essentially. It most often brings to mind things that happen in liquids and solids. I found this nice example in a journal of applied math with this nice quote that I liked. That a lot of our everyday experiences involve diffusion, such as brewing a cup of tea, and you can see these tea particles diffusing through the water. And here is just a numerical simulation of the same type of thing. And we can show from here that diffusion is essentially the result of atomic motions with kinetic energy inside some kind of material. And the result of that is essentially can be modeled as a random walk of particles through your material. And kind of averaged over all the possible random walks, we get material transport through a medium. So these are just 3 different numerical simulations of a random walk of a particle diffusing through a medium. And you can see that they've all kind of gone in different directions. They've all had slightly different details in their paths, but they've all ended up kind of moving a distance of about the same kind of distance. And so the main point here is just that diffusion can act to move atoms around throughout a material. We usually think of this in gases and liquids, but as geologists and planetary scientists, we also think about it happening a lot in solids. One thing to remember is that diffusion is a thing that's happening all the time, regardless of a temperature gradient. It's just actually the random motions of atoms inside your materials. In the presence of a chemical gradient, we can measure a chemical profile and have resulting evidence of that diffusion. So I'll just go on and talk a little bit more just to give us context here about why we care about so much about diffusion in Earth systems and planetary systems. It happens very slowly in solids, but over the lifetime of the solar system or over geologic timescales, it really matters a lot. And here's just a plot, an Arrhenius plot, just to orient ourselves. It's a plot of temperature here, the inverse of temperature here on the x-axis versus the diffusion coefficient or the log of the diffusion coefficient on the y-axis. So how fast these materials are moving around through sort of a range of materials that are important in Earth and planetary science. And you can see here that this range of diffusion coefficient spans more than 10 orders of magnitude, from solid things like minerals to liquids and the fastest things in fluids. But even the slowest diffusing things over millions or billions of years has quite an impact on the signatures that can be left behind. And we'll go through this again. We'll be looking at quite a few plots that look kind of like this. But the basic idea is that the diffusion coefficient, D, capital D here, is a function of temperature. Higher temperature makes things diffuse faster. It's also a function of pressure, P up there, and at higher pressures, things diffuse slower. And in planetary systems, it's a balance of those two variables that kind of determines the rate of diffusion. And here's just another kind of introductory point about this. Is again now is the log of the diffusion coefficient, so the mobility of things, and the distance, essentially, that those things can travel given a certain length of time where it's diffusing at a reasonable temperature. And you can see here that when you have things on the order of millions or billions of years, you can have, at high temperatures, diffusion on the order of centimeter kind of scale diffusion, which can have a significant impact. So generally in Earth and planetary systems, we can use diffusion in a lot of different kinds of physical situations that are happening, chemical zoning, crystal growth, etc. Today, actually, we're going to focus mostly on the closure temperature of isotopic systems. This is an important application of knowledge of our diffusion characteristics. If we have time, we probably won't. We could also talk a little bit about thermal reconstruction, very specific thermal reconstruction in iron meteorites. I probably won't talk about it today, but if I talk to any of you later and you want to talk about that, I have a bunch of extra slides you can see related to that. Okay, so like I said, we're talking about iron meteorites. Iron meteorites are the remnant cores of early planetary bodies forming in the solar system. And we feel like the processes that contribute to the formation and evolution of planetary cores in these early planetesimals and the terrestrial planets have things in common. We don't have any samples of our own cores, but we do have samples of iron meteorites that we can look at in much more detail, the chemistry of those things in much more detail here on Earth. So part of why we look at iron meteorites is to understand general aspects of core formation and core evolution in the growing bodies early in the solar system. Part of it is also to understand what was happening during that early time in the solar system. And here's just a picture. This is Gibeon. It's a 4A iron meteorite with a little sulfide nodule in it there. And basically, most of us know this. The iron meteorites, we feel, are the remnants of planetary cores that had differentiated in smaller planetary bodies during the early part of our solar system. Right, so today we're going to talk very specifically about two different radiometric systems that we can measure in iron meteorites. And there's chemical and isotopic signatures left in these iron meteorites that we can measure that give us important information about the timing and thermal history during their formation and evolution. So this is kind of where we're going to start. why we're looking at isotopes in iron meteorites. Way back, I guess, 60 years ago now, a seminal paper of measuring the age of iron meteorites using lead isotope dating, which sort of has opened the field of doing a lot of different isotope measurements in meteorites, not only iron meteorites, but all kinds of meteorites. So at this time, using radiometric dating that was newer at the time, they came up with an age of 4.55 plus or minus 0.07 billion years. And at that time, the age of the meteorites was indistinguishable from each other, and it was sort of assumed that all of the meteorites, the Earth, the solar system, everything was the same age within this level of uncertainty, which is about 70 million years. Okay, so that's kind of where this story starts. Over the last 50 or 60 years, there's been huge developments in isotope geochemistry, and higher precision, much more higher precision measurements have been able to be made, and now we have a much better resolved view of the sequence of events that was happening in the early solar system because we have much more high precision measurements of the isotopes. So rather than having just an uncertainty date on all of these things of 70 million years, which is basically including all of these events, we can start to distinguish between very specific events and processes that were happening during the early few million years in the solar system's history, right? So we're talking about iron meteorites today, and the current kind of idea right now is that the differentiation aspect of iron meteorites, so they're differentiated bodies, they're iron, and early on surrounded by some silicate mantle, happened in the first, single-digit millions of years. And ongoing evolution and metallic core crystallization happened not long after that, but still in sort of within maybe 10 million years of the birth of our solar system. And so now what we're really trying to do, kind of pushing the limit of how well we can understand this, is start to resolve different events within these 10 million year kind of range. And also, if anybody has questions and you just want to talk about something, you're welcome to raise your hand or interrupt me and ask a question at any time. That's fine. Right, so we're looking now at things that are happening early in the history of the solar system. The thinking has evolved in the last several years towards thinking that things were happening at a much more accelerated rate early in the solar system than sort of had been the view a while before that. And not only are we getting some of this information from our measurements in meteorites, but we also have recent actual observations of planetary accretion disks from ALMA that are also suggestive of things like planetary formation happening early in the life of these disks. And here's just a couple of examples where we have things that look kind of like our textbook examples of how we had imagined accretion disks to look like for a long time. But it's only been in the last 5 or so years that we've had direct visual observations of something like that with these gaps in the nebular disk and things like that that are suggestive of sort of early planet formation happening. And a sort of estimated age of some of these measurements is on the order of a few million years as well. So there's other lines of evidence that are suggesting that these early core formation and differentiation planet formation events were happening quite early in the history of the solar system. So today we're going to be talking about specifically stuff related to the lead-lead dating system and the palladium-silver dating system. One advantage of the lead-lead dating system that's been used a lot to measure the age of planetary objects and terrestrial rocks is that it can give us an absolute age, and these days at a relatively high precision. The advantage of some other isotope systems, in particular the palladium-silver isotope system, is that it's very short-lived and can give a very high precision measurement, but it's a relative age, so it needs to be kind of tied to an absolute age to put a good timeline on it. The other thing is that different isotope pairs pair with different physical processes that are happening during planet formation. So for instance, the hafnium-tungsten system that's been studied quite extensively lately kind of puts an age on the process of core segregation, or the time at which the metal component of the planetesimal separated from the silicate component of the sample that happens while everything is molten and at kind of a higher temperature. And these two isotope systems that we're talking about today are more connected with core crystallization processes that happen a little bit later in that planet's evolution and at a slightly lower temperature. And the idea is that, coupling these different isotope systems together can start to give you an independent idea of a thermal history. Okay, so this is where this project really kind of came from and started the inspiration for this project. There was a paper in 2010 using lead isotope dating on 4A iron meteorite called Muonionalusta. And in this paper, they quoted or measured an age of 4.565 billion years old. And at the time that was published, it was the oldest measured age on a differentiated meteorite that had been measured. And they did this by measuring the lead isotopes in these iron sulfide nodules inside the iron meteorite, because that's where the majority of the lead existed. Okay, so this date also supports the idea that planetary differentiation and evolution was happening very, very early, because this was a really, really old date. I will say right now, and if anybody wants to talk to me about this later, we can talk about it. I don't want to get into the main details of this. There is some question right now based on the assumption of what the initial uranium ratio was about exactly what this date is, okay? I'm not going to deal with that right now, but it's there. The point is, in some 4A iron meteorites, there's really old ages from lead isotopes, and we'll go from there. Okay, so now we know that we can measure lead isotope dates, and we can get some kind of an age from that, and what we really want to do is tie that age to something specific physically. And in order to make sense of our radiometric age, and many of you probably remember learning about this as students, that we require that all of the daughter atoms from that decay process are still present. Otherwise, we can't really ascribe a meaning to that age or that isotope ratio. So we need to do that. And the physical process that kind of determines whether or not those daughter atoms will remain in the crystal where they were produced is diffusion. So if the diffusion rate is too high of the daughter atoms and things are hot, and they can diffuse away, and they won't be retained in the sample, we won't be able to measure them, and we'll get an isotope ratio that doesn't make sense. So we need to understand diffusion, essentially so we can talk about the closure temperature, which is tying a temperature to the age that we measure using the isotope measurements, right? So temperatures below this closure temperature, the isotopes are all there, and that closure temperature is tied to the time that we measure. Okay, so that's what this whole project ends up being about, is that we need to tie this to a physical process, the closure temperature. At the time, they used a closure temperature for these lead isotopes in those iron meters of 300 degrees Celsius. Okay, so what that indicates is not only is this a very, very old age of the iron meteorite, that iron meteorite has also already cooled down to 300 degrees Celsius, so it's pretty actually highly evolved in its lifetime. by that moment. And they got this number, this temperature, based on experimental measurements of osmium diffusion in iron sulfide that was related to the closure of the rhenium-osmium isotope clock, which is fine because, well, it's not totally fine, but at the time it was fine because that was the only experimental data that was out there. There was nothing else to go by, and they wanted to have a closure temperature to quote, so that's what they did. But there's no real strong physical, chemical basis to think that lead is going to behave like osmium in this system at all. So that's where this project came in. We wanted to do experiments because I'm an experimentalist, so that's my approach. We did experiments to directly measure lead diffusion in the FES component that's in the iron meteorites. So we take a single crystal of FES, we polish it. That should say microns, sorry. And we bathe that small crystal in a surrounding source of iron sulfide that's doped with a little bit of lead. We are doing 1 atmosphere experiment in a sealed silica capsule. Here's a student, a high school student actually, Sherry Wong, who was working with us on this project sealing one of the capsules. And they're pretty simple experiments. You just run in 1 atmosphere furnaces for, I don't know, anywhere from a few days to a few weeks. And as we do that, the lead diffuses into the surface of the crystal. Okay, so we've been using a technique that is highly effective at measuring this kind of thing, but isn't the most popular technique around because it requires a big accelerator. And I'll talk about this for just a minute in case not everyone here is familiar with the technique of Rutherford backscattering spectroscopy. But basically what we do, we're working at pretty low temperatures, so our diffusion profiles are relatively shallow. They're on the order of about 1 micron or so, the entire profile. And so we sort of have a Rutherford backscattering is a technique where we can do a depth profile from the surface of that sample through the diffusion profile that we're measuring. And the way this works is we have a particle accelerator that can accelerate protons, but it can also accelerate alpha particles or helium nuclei. And we shine a beam of helium nuclei onto the surface of our sample. The beam is about 1 millimeter in diameter, so our sample's a bit bigger than that, and we are getting an average kind of integrated measurement over that millimeter. The helium nuclei, these alpha particles, come in, interact with the near surface area of our sample, and have an elastic collision with the nuclei at depth in our sample. And the energy at which those nuclei scatter back is proportional to 2 things. Importantly, it's proportional to the identity of the atom that it's scattering back from. So if it's scattering back from a high Z element with a large nucleus, it's going to scatter back at a higher energy than a low Z nucleus. And also, it loses energy as it goes deeper and deeper into your sample. So it loses a small amount of energy as it goes deeper and deeper into your sample. So what we end up with is this kind of spectrum where each of these ledges of the spectrum corresponds to a different element in our matrix. And because we have a pretty simple matrix, we're pretty lucky. This low Z element, sulfur, and then iron. And then we're also pretty lucky that lead is big and chunky and heavy and is going to be well resolved from the matrix. And this is our lead way out here. So we can resolve the lead pretty well. And then this part of the gradient here coming down is the lead as you go deeper and deeper into the sample. The concentration of lead goes down and down and down and down. Right? If this was homogeneously distributed lead inside here, you would see another flat ledge just like this. But because the concentration decreases as you go into the depth in your sample, we get this little gradient. And we can do some math and some data analysis, and we can basically extract a concentration gradient out of this gradient in the energy spectrum. And here's just a picture of my colleague, Danielle Cherniak, who runs the accelerator at the University of Albany, who's done a lot of these measurements with me. We also, Union College, I'll just plug for our department for a minute. We have a little accelerator ourselves, which is a great teaching instrument for undergraduate students that can come in and run this whole accelerator themselves because it's a little bit less cumbersome and easier to deal with. We just moved into a new building. That's why you see these like construction vehicles still behind our new lab. But we're also doing these same kinds of measurements in the physics department at Union College, looking at these things. So here we go. Here's an example of a spectrum. You'll see here we have our sulfur ledge, our iron ledge. And you can't really see it that great because there's not very much lead here, but there's a little lead peak here, and here it is close up. The blue line here is the fit to that data, and the red is the data points. And we can extract a concentration profile from that. And here's an example of what one of these concentration profiles looks like. You can see it's very, very shallow. This goes up to about 40, 50 nanometers into the sample. But it's very well described by the solution to the diffusion equation that describes a constant source of diffusant coming into our sample, which is just written up here. So the thing is diffusing the way we expect it to based on the geometry of our sample, and we can extract a diffusion coefficient from this analysis. It's all worked out pretty well. So we did this for lead. We did a bunch of experiments. And here's our data, finally. And here's the data from osmium, the initial assumption that had been made. And there's a couple of things we can look at from this plot. Okay, so the first thing is that this, again, is an Arrhenius plot. So this is the inverse of temperature versus the log of the diffusivity. So temperature is going down that way. And you notice the slope of the lead is much, much lower. So the activation energy of lead diffusion is much smaller. It turns out to be a pretty low number compared to some things, but it's actually very, very close to the value of iron diffusion in iron sulfide. So that gives us some confidence that lead might be substituting for iron, and maybe that makes sense. And here's osmium. So, well, there's a couple things. At about 300 degrees, just very ironically, they seem to be very similar. But because the activation energy is so different, the slope is very different, and at higher temperatures, they're different by several orders of magnitude. And this really matters when we're talking about kind of the cooling range that iron meteorites are going through when this is all happening is from about, here's the solidus, the FES solidus, roughly towards this. This is kind of the temperature range that we're going through. So that difference really matters, and I'm suggesting now that we look more closely at the iron, or the lead diffusion to guide us in our closure temperature. So I've gone through, I've done some also numerical models of how this diffusion works in a cooling iron meteorite. And these are numerical diffusion models I've been working on with Jim Van Orman at Case Western University. They're based on some old models that he had based on the hafnium tungsten system. But I've modified the code a little bit to work for lead. And this numerical diffusion model basically deals with that we have radioactive decay, so we have a constant new production of new lead in our iron sulfide. There's partitioning at the surface between the iron sulfide and the metal. There's diffusion of the lead in the sulfide. And we're assuming spherical grains and essentially a small amount of spherical FES grains in a large metallic body, which is what iron meteorites look like. And we can see here's a plot. We'll see a bunch of plots that look like this. Cooling rate of iron meteorites versus closure temperature. So this kind of covers a wide range from 1,000 or from 1 degree per million years to about 5,000 degrees per million years. The 4A iron meteorites, which is the group that this one specific example comes from, has cooling rates in the literature that range around 100 to 500 K per million years. So fast cooling meteorites. It's had a bit of a complicated history. We can see up around this range, these red lines are osmium, based on osmium diffusion, closure temperatures based on osmium diffusion. These blue lines are closure temperatures based on lead diffusion. You can see at high, fast cooling rates in large grains, in particular 2 centimeters, which was the size of the grain that this initial date had been measured on, the size of the FES nodule, we have a difference of about 300 or 400, excuse me, 300 or 400 degrees in the closure temperature. At very, very low cooling rates and at small grain sizes, this difference doesn't really matter as much. But at high cooling rates, and if you can find large grains, it does. The second important thing that we notice here is actually with large grains, at fast cooling rates, we can get closure temperatures that kind of start to approach the crystallization of that iron sulfide. So that's actually kind of an important moment in the history of a planetary core's life. Okay, so that's just what this says here. Fast cooling rates and larger grains, the closure temperature is much higher for lead. It can be closely pinned even to solidification of the iron sulfide. And yeah, we can use these dates in combination with others, including palladium, silver, and hafnium tungsten to start to get a picture of the sequencing of things. Okay, so here's just a couple of conclusions from this first series of experiments. They show that the closure temperature of lead can be quite different, and I would recommend that as people continue to try to do lead dating on iron meteorites, they refer to this type of a closure temperature. Instead, identifying large grains will allow us to actually pin to a physical process of solidification or close to that. And not only that, if these things are happening, if this closure temperature is happening at a higher temperature than we had said before, it's actually sampling a moment kind of later in that planet's life. Right? So this idea that we're measuring earlier things, where things are happening faster, can be kind of tempered with the idea that we're also measuring a higher temperature a moment earlier in that planet's life. Okay, now's a good time. Do you have any questions or anything you want to talk about? The solidus is around 990 Celsius. Yeah? Okay. So the second thing that we've been doing that's sort of related to this is looking specifically at the palladium-silver system and doing essentially the same thing, but now instead of looking at the lead diffusion, we're looking at the diffusion of the daughter product of this decay system, silver. The palladium-silver system has a half-life of 6.5 million years, so it's relatively short-lived. It can provide a very precise date, but it can only be a relative date. This system is really great in iron meteorites because it fractionates between the sulfide and the metal at first. So we can, usually the palladium will go into the metal component as that's solidifying, and the silver will remain in the sulfide. And then that palladium will begin decaying into silver in the metal. And so the silver in the metal is mostly a product of this decay, which is sort of a good context for using isotope methods like this. Okay, so we did something similar. We did diffusion experiments again. These are a bit more kind of traditional diffusion couple experiments that were measured using the electron microprobe. The one thing that was a bit difficult about these experiments is that actually, I was surprised by this when I first started learning about it, is silver is like super not soluble in iron at all. Here's sort of the iron-rich area of the phase diagram, iron-silver phase diagram, and this is atomic percent silver, and this is kind of the region you have to be in to get silver dissolved in your sample. I mean, there's not a lot of silver in iron meteorites either, so it kind of is fine. But that's probably why there was not a lot of information in the literature about silver diffusion in iron. So we did pretty traditional diffusion couple experiments, one side doped with a little bit of silver, one side just plain iron nickel alloys. These were done in the piston cylinder at Union College and also at RPI. They were measured using the electron microprobe. Here's an example of a resulting diffusion profile. It's on the order of a few hundred microns. And this fits, again, this black line or curve is our fit to the data, and it fits the assumption of a diffusion couple geometry pretty well. These were the first experiments I ever did in my piston cylinder at UNIT, so we did a lot of repeatability experiments, and our experiments are pretty reproducible, which was nice for us. And here is the Arrhenius plot of this data. So here again is the inverse of temperature versus the log of the diffusivity. And here's our new silver data up here compared to my PhD thesis data of a bunch of other things, not silver. We see the slope is very similar, but it's offset. Silver diffusion is actually quite a bit faster than a lot of our other siderophile elements, including palladium. And here's nickel diffusion down here, just for a reference. Okay, so because it diffuses faster, it might have a lower closure temperature than we had looked at before. The closure temperatures in the literature were based on nickel diffusion because there was no silver diffusion experimental data. I've been running the same kinds of models with the same sort of inputs as what I just described, and we've been trying to investigate kind of what are the controls on the closure temperature beyond just grain size and cooling rates. And I mean, this is basically grain size, but there's a couple other things there. But you can see grain size has a pretty big effect. And now we're talking about we're talking about diffusion in the metal, not the troilite. The silver is in the metal, and it depends on how far away from a troilite grain you are. So that's what these distances are here. And distance from a sulfide nodule. Okay, and you can get higher closure temperatures by measuring things farther away from a troilite nodule. And if you measure something close to a troilite nodule, that silver is still trying to get and able to get into the sulfide and diffuse away from the metal that it's in. So it depends on how far away from a troilite nodule you are to get a closure temperature as well as cooling rate. It also depends on the amount of troilite or FES in your sample. So here's two examples that can differ, not a huge amount, probably not even resolvable compared to the ages that we're measuring, but it is an effect on the order of 50 to 100 degrees, depending on the amount of troilite in your sample and how far apart each of these are from each other. Okay, finally, we can just talk for a few minutes about using these two things in conjunction with each other. And we have some idea of what's happening with lead. It's closing at a high temperature, kind of potentially close to the crystallization, the initial crystallization, or the solidus of iron sulfide. And then the palladium-silver system is actually closing a little bit later than that at a lower temperature. And the idea is eventually, if we have high enough precision data, we can start to untangle all of this. So here we have cooling rate versus closure temperature. This is our lead closure temperature. So at high cooling rates, such as what we expect in the 4A iron meteorites, we're up around 900 degrees Celsius. And here's the palladium-silver closure temperature. It's a couple hundred degrees cooler, maybe around 700 degrees Celsius, right? So they're separated by 200 degrees, which if you're cooling at 100 degrees per million years is 2 million years in time. So that information might be able to use to sort of disentangle some of the overlap or confusion between some of the ages that have been measured in iron meteorites, particularly the 4A iron meteorites. Here's kind of a bunch of text that kind of tries to access some of this a little bit. I have not totally really completed a full analysis of how to apply this directly to this whole suite of samples. I'm kind of working on that. That's where I'd like for this to go. But right now we have a sort of few general things that we can talk about. In particular, the 4A iron meteorites seem to have a complex cooling history. They probably lost their mantle at some point. There's periods of very, very rapid cooling. Right, but right now we have some lead ages that are very old and potentially consistent with something close to or not that long after the segregation that we know from hafnium tungsten isotopes. They're also less far away in temperature than we thought they were before. They're maybe only a few hundred degrees cooler. And even rapid cooling, we can get down to the closure temperature of lead within a very short time span of 1 million years or so. A slower cooling rate can get us from there to the palladium-silver closure at around 700 degrees Celsius. And there's something in this that I think doesn't get always used as much, this assumption that actually the cooling rate might be changing as well. Often we ascribe just a number of the cooling rate to these iron meteorites, but you know, even if it's just radiative cooling, that cooling rate is going to change as well as things cool. So to start to look at the cooling rate as a changing variable in these models is something that I'm working on still. All right, so yeah, here's some kind of very basic conclusions about this whole project as it stands right now. Closure temperature of silver in the metal. Oh, that should say lower. Oh, I guess I mixed that up, sorry. The closure temperature of silver is lower than lead in sulfide, and taking this into account and using these isotope systems in conjunction with each other can add some kind of more information to building up the timeline, constraining the timeline of the core evolution. And not only that, even though it will still be pretty low resolution, it could be seen as an independent way of looking at cooling rates in iron meteorites beyond the metallographic method, which is the sort of traditional method of looking at cooling rates. Okay, finally, I'd just like to thank all the people that have recently been involved with me in this project and support, et cetera. And that is it for today. Thank you. So we're not synthesizing we are using a natural pyrrhotite crystal from a Canadian mine, and we've measured it. It's not stoichiometrically FeS. It's about 0.9 something Fe, but we have also done some preliminary compositional measurements, right? So we've been trying to synthesize FeS at compositions ranging from 0.8 to pure FeS, and we haven't seen any changes, like any effect of that composition. The other thing is that the reason we chose the natural samples that we're using is that they are the same samples coming from the same mine that James Bernan used in his original study of the osmium diffusion. So we wanted to be able to directly compare the lead diffusion to the osmium diffusion in the same samples. Yeah, well, okay, so there's two things about, so here we go. So here, this is all taenite, right? And in chemisite, it's like really not. That's right? Taenite is gamma. And this is the solubility. But all of this diffusion and closure happens pretty much above the estimated nucleation temperature of the chemisite. Okay, so so even though the chemisite, like the nominal sort of phase boundary is sort of within the lower end of what we're talking about with our diffusion. But according to Yang and Goldstein and all these guys, that it was undercooled significantly before the chemisite nucleated. So the system had closed before that happened. Does that help? But the mass fractionation between the camosite and the taenite of silver isotopes. I mean, I guess it also depends on like what like how I mean, and this is not my area as much, but like how much metal is being dissolved. Like, is it an integrated sort of average over some camosite and taenite? Then that problem kind of doesn't matter quite as much, I guess. They're not that different. So I have been running these models with variable cooling rates. I can do that, and usually was sort of in the range of stuff that I've been talking about here, depending on what kind of assumption you use for nonlinearity in your cooling rate. Like I've been just doing an exponential kind of. It starts to, I think, only matter like at the really low temperatures. And it's only up 50 degrees. Like I think it's sort of less than what would be in the range of precision of the isotope measurements. But it's an interesting effect to sort of be aware of and deal with. And that's kind of the next step of some of this modeling when we're trying to investigate sort of a bunch of different controls on the closure temperature. And I think that the main takeaway here is that the closure temperature is not just a temperature. It depends highly on what part of your sample you're measuring and what you know about your sample and a lot of different things like that. Does that answer your question? No, I didn't do any. There's not much lead. Like content, like on actual meteorites, or. So we did sort of on our diffusion experiments, we were measuring concentration gradients of lead, but we didn't measure any background concentrations of lead in the sample before we diffused the lead in. I mean, it's below the detection limit of anything that we've been able to use, and the detection limit of the RBS is still like sort of parts per million level. I think it's very, very low. Yeah. Right, so we don't have any experimental data on lead diffusivity in the metal. But yeah, what we're looking at is, I think you're right that would control things, but the partition coefficient actually is important as well, and the partition coefficient is such that the lead is strongly partitioned into the sulfide, so that's where it's going to be concentrated, I guess. So we have right now, I think, an estimated diffusion coefficient, but we don't get much lead into the metal to diffuse. So really, it's mostly focused in the sulfide. It's also very important what the uranium partition. Right. It's not. No. It's lead. Lead can partition when once it's cooled and it's turned into lead and it's diffusing. So we take account to that. But you're right. Initially, the uranium partition coefficient is an important thing, and we have some experimental values. They might not be 100% appropriate, but they're the ones that are out there that are available between. We have some between metal and silicate and sulfide and silicate, and from that we can get a metal sulfide. So that's what I've done there. But you're right. It's the uranium partition coefficient is a super strong lever on the, yes. I think, no. I don't know. Let me think about that. Yeah. Yeah, it's in the sulfide. Yeah, sorry. I'm just thinking, yes. Yes. Right. Can I? Oh. I didn't get a chance to talk about this. But this is iron and nickel isotope fractionation by diffusion in iron meteorites, and I have that was published in 2016. It's not silver, but it's iron nickel isotope fractionation, and it's significant between taenite and camosite, and can have an impact on how we interpret bulk isotope fractionation values in iron meteorites. Pieces, yeah. I mean, I think that the basic idea is that it's like trapped late stage final melt liquid. It's after the crystallization. It's after the iron has formed. Because iron nickel forms at like 1600 degrees Celsius, right? So all the stuff that happens while there's still liquid sulfide is not part of this. This starts at like much lower temperature, around like 900, 950, once everything is solidified. I don't know. Uh-huh. Yeah. Right, before. Great. Thank you, guys.